Math 113, lesson 7.7 covers the dot product. So we've been working with our vectors. So let's start with two vectors. I'm going to call this vector A1I plus B1J. And then I'm going to call vector W A2I plus B2J, just so we can distinguish between the A and B. So the dot product looks like that. It looks like you're just saying V times W. But that's not entirely true, because if we were going to do V times W the way that these look, we would have to do FOIL, do all that distributing. But that's not what the dot product is. The dot product says we're only going to work with our coefficients. We're going to multiply those two A values. We're going to multiply those two B values, and then we're going to add that together. So the sum of the product of A times A and B times B. So this would be our dot product formula. All right? So if I have two vectors, let's say I have vector V is 7I minus 4J, and vector W is 2I minus J. And I want us to find three things. We're going to start by just finding the regular dot product V dot W. All right, so if we use that little formula, we're going to multiply 7 times 2 plus, now that first B value is negative 4, and that second B value is negative 1. So I get 14 plus 4 would give me 18. So V dot W is 18. All right. If I ask you to do W dot V, let's see if we get the same thing. All right, so W, my first A value would be 2, and then the A value in V would be 7, plus negative 1 times negative 4. It doesn't matter the order you write them, because it's saying W dot V. And we get 14 plus 4, so we do still end up with the same solution. All right, one other question here. If I said, let's do W dot W. Okay, so then I'm multiplying 2 times 2 plus negative 1 times negative 1. And I get 5. So W dot W is 5. All right, so there's our dot product. Now with dot product, let's talk about the properties that are involved. If we have U, V, and W are all vectors, and C is a scalar, which is just a number. All right, so our properties would say things that you can do with dot products. U dot V, we just proved it. It is the same thing as doing it the other direction. U dot V is the same as V dot U. So it doesn't matter. Those are the same either direction. So there's our first property. Our second property says if I am trying to do the dot product, oops, that did not look like a V. All right, if I'm trying to do this dot product, it does essentially sort of look like distributing, but it is not entirely distributing, because it's U dot V plus U dot W. Now remember, dot is not the same thing as just multiply, so you got to use the rule for dot product. Right? If I multiply some vector times 0, I do get 0. when I multiply a vector times itself, like we did up above, we said W dot W, not multiply, W dot W. Here's what we get. Do you remember what this notation stands for? That stands for the magnitude. Remember we talked about magnitude. All right, so V dot V gives us the magnitude of V. And then the last property says if you're multiplying one of the vectors times a scalar, and then you want to do the dot product of V, you can really move that scalar around, do the dot product of the two vectors, and then multiply that answer times C. Literally multiply, that's not a dot there. Or you can multiply the other vector times the scalar and then do the dot product. So just be careful when you see that dot, don't just assume multiply, okay? That dot, when we're working with vectors, means dot product. So we have to use that little rule every time. All right, we will often be asked to find an angle between two vectors. And so there's a formula for that. Our angle, we're going to call it theta. So the cosine of our angle theta is found by saying V dot W, the magnitude of V, times the magnitude of W. Okay, so theta is our angle between vector V and vector W. I'm not sure why things keep disappearing. Okay, so theta is between U and V. Between V and W. So here's our little formula. The cosine of theta is found by saying V dot W, and then the denominator that says magnitude of V times the magnitude of W. Up here, when I use that word magnitude, I should have said magnitude squared. Okay, so that's how we find the angle between two vectors. So let's practice that. Let's find the angle between V, which is 4I minus 3J, and W, which is I plus 2J. All right, so let's find theta. All right, so the cosine of theta, remember we're going to do V dot W, so that's 4 times 1 plus negative 3 times 2, divided by, remember the magnitude of V is found by doing the square root of A squared plus B squared. Okay, just a little reminder there. All right, so the magnitude of V is going to be the square root of 4 squared plus negative 3 squared. And the magnitude of W would be the square root of 1 squared plus 2 squared. All right. So my numerator gives me 4 minus 6. My denominator, I get the square root of 16 plus 9 times the square root of 1 plus 4. I get negative 2 over the square root of 25 times the square root of 5. Now I can do the square root of 25, so I'm going to. Now, no need to rationalize this denominator because this isn't our answer anyway. So no need to rationalize. We're looking for theta, the angle. So we're going to do the inverse cosine of this fraction that we just found. So make sure you type that in your calculator correctly. Go ahead and give that a try before I write the answer to make sure you get the same thing I do. we're going to round our answer to the nearest tenth. Hopefully you remembered your calculator should be in degrees. And we get 100.3 degrees. That would be the angle formed by these two vectors. Right? Right, we have two little vocabulary words to talk about. Parallel vectors. Now we know that means that their slopes would be the same, but what else does that mean? If we have two parallel vectors, that happens when theta is 0 degrees or when theta is 180 degrees. Now remember, theta is the angle between the two vectors. Okay? All right, and then we have orthogonal vectors. Okay, orthogonal vectors, you know that two vectors are orthogonal when theta, the angle between them, is 90 degrees. The angle that they form is 90 degrees, which means the dot product of these two vectors, these two orthogonal vectors, is 0. Their dot product is 0. Okay, another word for orthogonal vectors is perpendicular. So just in case my math lab throws those words interchangeably, they do mean the same thing. An orthogonal vectors, two vectors that are orthogonal, have a dot product of 0. The angle they form is 90 degrees, and we call those two vectors perpendicular. So you may have a question that looks something like this. Are the vectors orthogonal? And I'll give you the two vectors we're talking about. 2i plus 3j, 6i minus 4j. And so my question is, are they orthogonal? So to answer that, you do the dot product. If we do the dot product and we get 0, then our answer is yes. All right, so we get 2 times 6 plus 3 times negative 4, 12 minus 12. All right, my dot product is 0. That's not my answer. The answer to the question is yes. They are orthogonal because their dot product was 0. All right. Now, the whole reason we learn vectors is so that we can actually do physics. Realistically, that's the reason we have vectors, so we can do physics problems. So, a very common physics problem is about work done. Okay, the amount of work that is done, or work done by the force. So, work done. Here's what you need to think about. Work, we're going to call capital W. Done by a force. We're going to call that force capital F. Moving an object from point A to point B is described using this formula. All right, there's our formula. Work is equal to the force times the vector, A to B. Now, when we do this in a word problem, here's what we're going to do. That force, we're going to use its magnitude. That vector, we're going to use its magnitude, and then we're going to multiply by the cosine of the angle. All right? So that's how that translates into what can we do. All right, so this magnitude of the force okay, this vector AB, remember we were moving from point A to point B. So this is going to be the distance over which a constant force is applied. Don't tune me out if you're not interested in physics. We can all do this. And theta is the angle between the force and the direction of motion. Okay, so make sure you jot down that formula. And I'm going to show you how we're going to use it. It's really not going to be difficult. Even if you're not even remotely interested in physics, this is not going to be difficult. All right, so I'll leave that formula where we can see it. All right, so here's our last example. We're only going to do one of these. All right, so we've got a child that pulls a wagon. Okay, that's a simple physics problem. Pulls a wagon along level ground. Easy enough. By exerting a force of 20 pounds on a handle, that makes an angle of 30 degrees with the horizontal. So you can imagine a child holding the wagon handle, and they're not holding it up real steep because it's only forming a 30-degree angle. We're not going to draw that. How much work is done pulling the wagon 150 feet? That is 150. How much work is done pulling the wagon 150 feet? So we're going to use that formula that's right above. Now I'm going to have to move the screen up. So you should have that formula beside you. Okay. So we are asked to find the work done. That's capital W. All right. The magnitude of the force. Okay, it said that the child was exerting a force of 20 pounds. So the magnitude of our force is 20. And it said that the handle made an angle of 30 degrees with the horizontal. So we've got cosine of 30 degrees. The question was, how much work is done pulling the wagon 150 feet? So that's from point A to point B, the distance. That literally is what we're going to do. Just that simple, guys. So the hard part's just the formula itself. All right, so I'm going to multiply 20 times 150. I get 3,000. Now I know that the cosine of 30 is the square root of 3 over 2. So I end up with 1,500 times the square root of 3. Go ahead, and I think my math lab is going to want you to give a decimal answer, or it might say round to the nearest whole number. We're going to go whole number on this one. 2,598 foot-pounds. All right, work is not just in feet and it's not just in pounds, it's foot-pounds. We went a distance and we had a force. So that's why we have to say foot-pounds. All right, so that is lesson 7, our dot product and our work done. And all of the work problems that you have are going to be similar to this one, so I don't want you to think it's going to be like some variety of questions that all say something way different. They're not. They're all going to follow this same general format. So let me know if you've got any questions.